Okay, welcome to the first colloquium of the semester. And also for the first years, welcome to the School of Astrophysics once again. As we have told many times, we will have this weekly colloquium every week on Wednesday at 6:45 in most Wednesdays. Sometimes there may be some unusual time or day. So, so today we are happy to welcome Dr. Arko Chandra from the Shah Institute of Nuclear Physics. Professor Chandra did his undergrad from Jadavpur University and went to IIT Kanpur for masters. Then from there he went to Florida State University in the US for his PhD, and then did two jobs, one in Valencia in Spain and another in the Weizmann Institute in Israel. And then he joined SINP in 2024. So Professor Chandra is an expert on particle physics, particularly in experiments and instrumentation. And he will talk about his research work. So Arko, welcome.
Okay. Thank you, Ridhuvanda, for this nice introduction. And it was a pleasure to come to Presidency University. So I visited this campus as a student. First time I'm visiting this campus when I'm on the other side. That's a different feeling. Anyway, so this is the School of Astrophysics, but I will show some work from my particle physics background, which I did in the last couple of years. So this is actually a work in collaboration with the Weizmann Institute, where I did my postdoc, the second postdoc. So today's talk will be based on these two papers, and this is in collaboration with the Weizmann Institute, Noam, Sasa, Roman, Nathalie, Alon, and others. So the title is The Quest for the Nonlinear Breit-Wheeler Process. So I will try to explain what this is and why we are interested in such quest. So I tried to make a very accessible outline of this talk. So, okay, so this is the outline of my talk. So it will be the beginning, the middle, and the end, the as simple as possible I could do. And then in the beginning, I will talk about the theoretical motivation. So I will tell you what is nonlinear Breit-Wheeler production and why this is important. Then I will talk about the experimental procedure, so what we have done and why we have done that. And finally, the end goal, like what is the outlook. Okay, so before I go on, so let's look at a very simple theoretical situation. So we have vacuum and we are applying electric field to it. Okay, so vacuum, as we know, so vacuum is not actually vacuum. We can have electron-positron pair coming out of the vacuum. But if the electric field is sufficiently weak, then the rate of pair production should be the same as the rate of pair annihilation. So what does that mean? That vacuum stays vacuum and nothing interesting is happening. But if the electric field is sufficiently strong, okay, what will happen? This electric field, it will pull the electron-positron apart, right? So in a sufficiently strong electric field, vacuum will start boiling. So it will give rise to electron-positron pair all on a sudden. So this is spontaneous pair production coming out of vacuum. So this is actually a theoretical prediction. Of course, you understand it can happen because if you have sufficiently high electric field, you can keep the pull the electron-positron apart. But we don't see this every day. Why? Because the electric field at which vacuum starts boiling, so this is given by Swinger critical field, and this value is of the order of 10 to the power 18 volt per meter. So this is a huge number, and it is not possible to achieve this electric field in terrestrial laboratories. Okay, but nowadays, I mean, we have strong lasers. So the atomic physicists, so they have made some very, very strong lasers. So lasers will come with its own electric field. We can use the electric field of the lasers to go to the Swinger critical field. But I will also show that this laser field may not be enough to go to the Swinger critical field, and that's why we particle physicists are thinking of something else. I mean, to add something else to lasers so that we can go to the Swinger critical field. So this is actually, this field of research is called strong field QED. So strong field, you understand, this electric field is very, very strong. And this is like quantum electrodynamics because we are dealing with electron, positron, lasers, etc. And this is the brief history of brief history of this field. So theoretical discussions started in 1930s by Schroeter, Heisenberg, and Euler. And Swinger calculated his critical field in 1951. And experiment 144 at SLAC, so that tried to approach the critical actually to that. And since this is like non-perturbative, so theoretical predictions are very, very difficult to give. So experimental approach is currently the only way to understand what is happening in the well, laser and electron beam. So yes, yeah, I'll actually come to that. I have a slide. Yes, so I'll discuss that. Okay, so the experimental data will help understand the field better, and we will understand this type of extreme region in a better way. Okay, so now I talked about lasers. So this is the world map of high power laser facilities. So high power laser means more than 0.1 petawatt. So different colors show different power classification. And you can see there are many laser power facilities in the US. There are some in the Europe, in South Korea and China. And in TIF, I mean, well, these are not visible. So this is TIFR Hyderabad. So they have a Trishul laser facility. So that is like 1 petawatt laser. And then the world's highest power laser is now at LINP. So this is in Romania. So they have a 10 petawatt laser. Okay, so these are very, very high power laser. And just to give you the context, how high this power is. So I have one slide to tell you what is there. So this is the power calculation. So the energy divided by the time, the pulse length of the laser. So 10 petawatt is the power of laser. But when I look at the West Bengal peak power requirement, so that was in 2025 during Durga Puja. So this value was 12.5 gigawatt. You see, from gigawatt, this is petawatt, 6 orders of magnitude high. Okay, so you understand like petawatt is so much higher. Okay, and then Kolkata peak power requirement is 2.7 gigawatt. Of course, so it's not at all close to this value. Now, if I have this power, so then we can have this intensity. So intensity is divided by the power divided by the area where we focus the laser. So laser is, I mean, this is cartoonishly, we have shown this as a Gaussian distribution, but there are some aberrations to it. But we can say that we can focus the laser in, say, 2 by 2 micrometer square. So given this P of 10 petawatt, the I is around 10 to the power 23 watt per centimeter square. Okay, so now this is my I. Then we can use the electric field from this formula. We can get that. And now let's see. So I already said this is 10 petawatt laser. So what is the electric field that we can get out of it? So following this formula, the electric field comes out to be 10 to the power 15 volt per meter. Okay. And what I said that the Swinger critical field is 10 to the power 18 volt per meter. So then how can I go to the Swinger critical field? The obvious choice would have been to increase the power to another 6 orders of magnitude. Okay, but you understand, so that will be enormous. I mean, I don't know if within the next 50 years we will have that much high power laser. So there is this gap of 10 to the power 3 volt per meter in electric field to go to the Swinger critical field. So here comes particle physicists like us. So until now it was like laser and other things, but now comes particle physicists. So why? Let's consider this situation. So this is the yellow region is where we have the electric field, and then this is like electron positron coming out of the vacuum. So this is the Swinger pair production, and the probability is given by this. So this is the Swinger critical field divided by the critical field, and here pi is a constant. But now consider, I mean, here you understand like this epsilon has to be of the order of critical electric field so that this probability becomes measurable. Okay. Now consider second situation. So we have an electron beam that enters the region where we have electric field, and under the influence of the electric field, this electron beam can give rise to Compton scattering. So this is we call it nonlinear Compton scattering, and then this photon can give rise to electron positron pair. So this process is called nonlinear Breit-Wheeler pair production. So if you forget everything from this side, then if you only focus this, so then this is very similar to what we have in the Swinger pair production. But of course, like this is not exactly the Swinger pair production. This is the best we can do to mimic the Swinger pair production. Okay, so and now if you look at the rate, so this rate has now one important factor, 1 over E by M. So this is the boost. So this is the gamma of the Lorentz transformation. Okay, so now you see this epsilon, I mean this electric field, this can be multiplied by this gamma, and then this gamma, if I have very big gamma, say 10 to the power 3, 10 to the power 4, then the gap that we had, this 10 to the power 3 volt per meter gap, that can be overcome. Okay, so this is how we want to kind of understand the strong field QED region, because this is not possible right now, but this is possible because we have a boost factor coming from the electron beam, and that can help us to go to the Swinger critical field. So this is the thing, this nonlinear Breit-Wheeler pair production. So this Compton photon decays to electron positron pair. So this is what we want to measure in our experiment. We want to understand like what is the rate given the electric field, etc., and how it changes. So those values will be important for theoretical modeling. Okay, so yes. Okay, so nonlinear in the sense that when do I say linear? So linear means we have, say, electron beam, and then say one photon interacts, then two photon interacts, three photons interact, etc. So these are like linearly interacting, and you can have some perturbative expansion on that. But when I say nonlinear, so that means all the photons, so the laser density is so high, the photon density from laser, they interact, so many photons interact that you cannot do this linear expansion on a number of photons interacting. So you have to consider all the photons coming into the electron beam, and that's how you
talk about in lasers.
Maybe it's very similar to that.
Like one electron and one photon is interacting with.
Yeah.
Bulk photon interacting with the bulk electrons.
Yeah, bulk photon interacting with bulk electron, and these photons are pretty energetic photons.
Yeah. So these photons can go up to GeV.
Yes, very high.
Yes.
Much higher than the mass energy of the electron.
Yes. Yes.
So I mean, I'm trying to understand that how is this different from a typical Compton.
Okay. I'll show some slides. Okay. So now we understand that we need electron beam and the laser electric field. So this is basically the nonlinear Compton process followed by the Breit-Wheeler process. So this is the Feynman diagram, and then this is like cartoon so that you can understand. So from one side we will have electron beam, and from the other side we will have high power laser. So for the electron beam, we use the electrons from FACET setup. So that is in Stanford Linear Accelerator Center in Stanford, and they can go up to 13 GeV, but at present they can go only up to 10 GeV. And then the electron bunch is 2 nanocoulomb. So they have something around 10 to the power 10 electrons per bunch. And on the other side, we have this high power laser. Right now it is 10 terawatt, but we eventually will go to 100 terawatt. And under the influence of the laser electric field, this is the Compton photon, which gives rise to electron positron pair. And then E over m, what I was talking about. So if E was 10 GeV and then m is the mass of electron, 0.5 MeV. So you see this factor is 10 to the power 4. So now we can close the gap of Swinger critical field, and in fact we can go beyond. Yes. This is electron photon scattering. Yes.
Now, there in the scatter, there is only one gamma.
Yes. 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 So this is inverse Compton scattering. So suppose this is electron, and then there are like say 3 laser photons, and then they interact, and then this the energy of these 3 laser photons will be combined into this one photon that is going out. Okay, but yes, wait. So this is like in that regime where we can do perturbative expansion. So where I can say like 3 laser photons interacted. That's why we get this type of output of this photon. But there can be some places where we cannot do it like that. Okay, so in that case we have to solve the Dirac equation under the external electric field exactly, and that can be done only for plane wave and Coulomb potential. So that is actually when I showed here. So I wrote these are Volkov. So these are like Volkov electrons. So that is the solution of the Dirac equation when I have the external electric field added. Feynman diagram is a well. So okay. So actually, I think I have the. Can I go to the backup now? I have the. Okay. All right. All right. So when I draw it like that, so this is actually Volkov electron. So if there can be 2 scenarios. One where the perturbative, where the coupling is very, very less than 1. In that case, this Volkov electron can be written in like this, where I have this electron line and then these are the photons interacting. But where the case that we have coupling to be higher, like of the order of 1, then we cannot draw it like that. So then this electron has to be written as like Volkov electron. There is no perturbative Feynman diagram like this.
Also, if you like, you can move the chair.
Oh, okay. All right. Okay, so now a little bit more into this electron laser collisions. So this first one is the nonlinear Compton scattering. So here you see I have drawn this Volkov states, but then this is equivalent to that n number of photons. But this can be done only when I have coupling or less than 1, very, very less than 1. Otherwise, this would not exist. We have to show it only like that. And this is the nonlinear Compton scattering, and then this is the nonlinear Breit-Wheeler pair production. And there are 2 parameters. One is the laser intensity parameter, A0. So this is given by this. So E is the electric field, omega L is the laser frequency. And then other one is the quantum nonlinearity parameter. So this is defined like chi, like this. So now this A0, okay. So now look at this diagram. So this is the electron on inside the laser, and then this electron can radiate photons. So that is the Compton photon. And here the coupling is alpha, the 1 over 137, the good old alpha that we have, not a problem. But then look at this line, this double line. So this can be shown like this, where we have a single electron and then many, many laser photons interacting with it. Here the coupling is actually A0. So this value that I am showing. Now this A0 is now, this is like ratio of electron field divided by Swinger critical field. If I get electric field of the order of Swinger critical field, then this A0 is of the order of 1, and then this cannot be perturbative anymore. Okay, and then the quantum nonlinearity parameter. So if chi of the order of 1, so then the quantum effects come into play, If chi is very, very less than 1, so then we have Thomson scattering only, like the classical scattering. Okay, so since this is a school of astrophysics, so I just have added one more slide. So this is the strong field QED in astrophysics. We can find that around magnetars, but for magnetars, it's not electric field, it's the magnetic field. So magnetars can reach up to say 10 to the power 14 or 15 Gauss, I think. And then the critical field, Swinger critical field in magnetic field, so that is around 10 to the power 13 Gauss. So basically, if you go very close to the magnetar, so then we have the region for strong field QED test. Okay, and this actually a paper. This is not from us. So this I got it from arXiv. So it showed that how a magnetar can help to understand the like coherent emission of photons. So this is like electron which moves because of the magnetic field line, and then that can decay to photon, and then this photon can give rise to more photons, etc. But this is, I mean, when I showed this slide to Pratikda, so Pratikda told me like, do you know if anybody is searching for SFQED in astrophysical observation? And I could not find any. So maybe this is a very, very new field. And this paper was like last year, published last year.
Magnetars are not very common.
Yes.
They are
Hmm.
these kinds of things also, I mean, difficult.
Yes.
Some sort of indirect
Hmm.
observational method. Because these are not experiments that you are doing
Yes.
in your lab.
Yes.
But yeah, you see, these are known issues, but they are well known.
Okay, so this is the E144 experiment in 1999. So here, this is the y-axis. This is the number of positrons per laser shot as a function of A naught, and you see like they could reach only up to 0.35. And here, the number of positrons, this rate increases as A to the power 2n. Here they found n to be something around 5. So this was still perturbative because A naught was less than 1, and this was well described by theory. And well, this was like the first experimental try to go to the strong field QED region, and that was in 1999. And this is actually a very busy plot and little bit ugly. I apologize for that. So x-axis is the laser intensity parameter A naught. Y-axis is eta, which is actually chi divided by A naught. Now, what do you want to achieve? So we want to go to higher A naught so that we get non-perturbative regime. We also want to go to higher chi so that we get the higher quantum effects. So basically, we want to go to this direction. The previous experiment E144, it was located here, so it was still perturbative region. But anything beyond, say, this greater than 0.5 or so, this is like non-perturbative. And there are few experiments proposed. So LUXI 1. So I actually worked as a postdoc in LUXI, and now I work in this E320 experiment. And NA63 is an experiment at CERN. So they have already published their data. So these are still, I mean, there are more experiments coming up, such as Apollon in France, then Corels in South Korea. And then this region, which is more than chi equal to 2000. So this is like fully non-perturbative. And here, I mean, no theory, no model, etc. exists. So this is like terra incognita for us. But I don't think we will reach this region in, say, in 2-3 decades. So we are still in this region. Okay, so then I think, yeah, so now I just want to show you what are the challenges. So as I said, the electron beam, so we have 10 to the power 10 electrons, sorry, we have 10 to the power 10 electrons coming in. Not all of the electrons will interact and give rise to photons. So maybe say 10 to the power 8 photons are created, and then out of those 10 to the power 8 photons, only say 10 to the power 2 positron or electrons will be produced. Okay, so now you see, like if I want to search for this electron, so of the order of 100 electrons, but I start with 10 to the power 10 electrons. So electrons will be swamped by the background, like too many electrons coming from the beam, so that we will miss this signal. But if we look for positron, so then positron can be separated out from the electron just using magnetic field. Positrons can be also background, so I mean coming from background, and I will tell you how we get rid of the background positrons. But for us, like if I am an experimentalist and I am told to measure the rate of interaction here, the easiest thing is to find the positrons, like how many positrons we are getting from signal from background, then we can we understand the rate. Here, if you tell me like why don't you find electron, I would say no, I cannot do it. Okay, so now the challenge is we have 10 to the power 2 positrons at most, but we have so many background. So how do I search for such a tiny signal amidst a very high background? So we are like particle physicists at CERN, we have done that quite a lot of time. Well, we only found Higgs as a signal, but like there are other techniques to search for signals. We could not find any new signal, but anyway, so this is like our expertise. So if we have a very low signal rate and very high background, we can make some detectors. We can reconstruct the hits from the detectors so that we can extract the very low signal rate. So that is how like particle physicists enter this strong field QED experiment.
The background positron count.
Yes, so it will come from how it comes. I'll come to it later. All right, so then I think, yeah. All right, so first part is done. So now I will talk more about the experimental procedure. Okay, so you understand. So for this type of experiments, we need at least a very high energetic electron beam, and then we need very strong lasers. Okay, so we have to basically collide both of them. So there are a few places in the world where this can be done. So one is at the SLAC. This is the Stanford Linear Accelerator Center. So they have a 10 GeV electron beam, and at present they have 10 terawatt laser, but they want to go to 100 terawatt laser. So there are some pros and cons here. So pros, that the electron beam is very high quality. It's like very monoenergetic, almost like a pencil. And then the repetition rate is very high. And here we can go chi of the order of 5. But one problem is it is difficult to sync the collisions. Why? Because we get the trigger from the linear accelerator, and we don't have very good idea about when the laser when the electron beam is passing through the laser. So there is always some like time lag, even if it is a nanosecond time lag, that is a lot here. So that is pulse laser, yes. So and then the laser pulse is also very small. It's like femtosecond. So it's a huge challenge to synchronize the collision. So what we do, so we have some diagnostic setup which tells us if a collision happened or if a collision did not happen. So we try to see the Compton photon, like if the Compton photon rate is higher for some collision, then we will say that maybe we have the collision there. Otherwise, like just looking at the trigger, it may not be a right way to understand the collision. And then the other one is where we use all laser solutions. So we don't have an electron beam. So we use the laser to accelerate the electron. So that is like LWFA, so laser wake field acceleration. And so the same laser is used to accelerate the electron, and the same laser is used to create the electric field. So there the synchronization is very easy. Okay, and this is the only pro here. So there are many cons. You see, these are all red. So the electron beam is very bad quality, and I will show you like. And then the repetition rate is 1 per minute. So this is also not very good for us if we want to take more data. And so here the reproducibility is a problem. No. This is quantum parameter, quantum nonlinearity parameter. Okay, so now I talk more about the E320 experiment that we are doing. So this is the electron beam coming, and this is the interaction point. So we have the laser here, and this is the interaction point chamber. So we call it picnic basket. And then after the collision, so we will have so electron, photon, and positron. So they will all come out in this beam, and we have 3 quadrupole magnet to focus those beams, and then 1 dipole magnet. So because dipole magnet, they can separate electron and positron. So positron goes this way and electron goes this way. And then, so if I want to detect positron, so we will keep a positron detector here in this region, because of the dipole magnet, positron goes that way. And then photon will be undeflected by the magnetic field. So the Compton photon will go in a kind of a straight line, fall into a dump, and then photon can give rise to many background particles. So these are some parameters. So we have 10 hertz rate, so 5 for collision and 5 for in situ background. And with the 10 terawatt laser, we expect A naught to be 425 and chi of the order of 0.5. And when we upgrade the laser, then we can expect A naught of 10 and chi of the order of 5. So now, what are the signal rates? So this is actually a simulation that I did. So this is with a Ptarmigan simulation software. Of course, these are like simulation software. So approximations have been done here. So this is A naught, and then y axis is the positron rate. For A naught 425, we expect say 10 to the power minus 1 or 10 to the power minus 2 positrons per bunch crossing. So bunch crossing means the event here. So that means if we get 10 events, out of those 10 events, we expect 1 positron coming from the nonlinear Breit-Wheeler mechanism. But how large is the background? So you understand that signal rate is low, 10 to the power minus 1 per event. How large is the background? So talking about the devil is here. So you see, this is only, I mean, this is Jan4 simulation. 5 electrons passing through the beam line, and these 5 electrons can create so many, like this green are gamma, and then the gamma can give rise to again electron positron pair, etc. And this is only 5. And how many electrons are we dealing with? 10 to the power 10. Okay, so you understand the extreme challenge. So our signal rate is 10 to the power minus 1, and our background can be as big as 10, and in fact 1 can give rise to so many. So then you have to multiply by that. So
the energy range you are to.
Yes, that is true. That is true. And yes. Yeah. So yeah, that is how we finally get rid of the background. All right. So now, what is the solution? So the solution that we proposed, we use multi-layer pixel tracker detector. So what is it? I will come to it. So we have 4 layers, or I mean, in the prototype we used 5. So these 4 layers, so this can help us to get rid of the background tracks from the signal tracks. And how it can be? So of course, this will be what I will show in today's talk. Okay, so then this is the SLAC linear accelerator. So this is like 2 kilometers long, and this is our detector prototype. I'll come to it later. And this is the region. So this is the dipole magnet here, and this is the region where we will keep the tracker detector, because positrons will go in this way and electrons will go in that way. And this is a small video of going to like SLAC underground. So this is like 30-meter deep underground, and it stops at the picnic basket. So this is the interaction point of the laser and the electron beam. And well, so there are many other experiments are going on in the same place. So there are many other apparatus and detectors, and so that's why it is a very busy area here. Okay, so now let's talk about the tracker detector. So we use Alpide pixel chips. So Alpide is Alice pixel detector. So this is made by Alice experiment at LHC. So Alice is using these Alpide chips for their ITS-3 detector setup. So this is highly granular pixel chip. So this can have a position resolution of 5 micrometer and highly efficient for say charged particle, but it is actually blind to the photons and neutrons. So the photons that I showed in the previous simulation diagram, you see most of the photons will not actually hit our detector. So that actually saves us a lot. And then so this is the actual active area. So this is 13.8 by 30 millimeter square area, and these are like relevant detector electronics. So this chip, I mean, this is one chip, but then when I go to this bar-like structure, so this is we call stave. So there will be 9 such chips located, and so that actually increases the detector coverage area. And then to reconstruct it, so we use combinatorial Kalman filter. So there will be 4 layers, and we will have hits from all 4 layers. And we need to reconstruct the hits using, say, straight line, because the region where we keep the detector. So this is actually outside of the laser. I mean the magnetic field, and that is why, like, if we have a positron or electron, so they will go in a straight line. Sorry? No. These are not. And then after, I mean, we have Kalman. So we actually start from this, and then we go in the forward direction. We reconstruct it, and then we also go back in the backward direction. And that's, I mean, there are 2 passes, and that's how we select the tracks, signal or background. Well, I'll again come to it in a detail later. And this is the after selecting the signal tracks, we can get the energy reconstruction for different tracks. Okay, but when we want to use Kalman filter algorithm, it requires detailed knowledge about the setup alignment. Also, we need to know the input. I mean, we need to have a guess of the input momentum of the track. So these are the problem if you want to use the Kalman filter. Okay, so now I will show some simulation studies. So this is from this paper with the full tracker detector. So that means the detector has 9 chips. Okay, so then these are the steps. So that means 9 alpides. These are kept in 4 layers. And then, so now see what is happening here. So then if we have a straight, I mean, if we reconstruct a straight line, and then this straight line goes back to the interaction point. Of course, we need to take into account how it will be bent inside a magnetic field. Then we can say that this track is coming from signal. But what about background? So if I show you again, so you see this is the signal. So the signal generates from an interaction point. So signal has some directionality. Okay. So if you reconstruct the track from multiple hits, and if the track has a directionality and it goes back to the interaction point, we will say that this is the signal positron we are looking at. Okay, there are again ifs and buts, but I am not telling it here. But for background, you see background can come from any random direction. So that's why, like, the background tracks, if you reconstruct the background tracks, they should not point back to the interaction point. Well, they should not point back to like any proper location. So it will be basically random. So that is how we get rid of the background tracks from the signal tracks.
Or beyond the interaction.
So if, well, so no, the nonlinear Breit-Wheeler positrons that we want to detect, they will come from the interaction point.
They come from the but the positron that you have detected,
yes,
can start from anywhere in the interaction path.
Well, maybe. So you are saying, like, say this is the interaction point, and then some positron was created following the path of this. That can happen. So yeah, yeah. So that can happen. So that's why we cannot just say, I mean, we cannot just find one positron. We have to find many such positrons, and then we have to do a detailed analysis to understand if it is really the NBW positron or it is something else. Okay, so this was the reconstruction chain. So we used GN4 simulation, and then we had to cluster the heat on the pixels, and then we reconstruct the tracks using, say, Kalman filter algorithm. And this was like the tracking efficiency. We get around like 90% efficiency at 3 GeV of energy. Okay, so now remember this was the signal rate I showed. So our expected signal rate is 10 to the minus 1. And now if we look at here, so this is the reconstruction of tracks coming from only background, and this is our signal rate. So when we have nominal background, so the background track reconstruction is 10 to the minus 4, whereas our signal rate is 10 to the minus 2. So this is well above the background rate. Even if we consider a very sinister situation, we have like 10 times more background. Even then, the signal rate is higher than the background rate. Okay, so now I'll talk about the experiment that we have done. This is from this paper. So this is the Alpide chip that I showed you, and then we have an Alpide card adapter. So we keep 5 layers. So one here, and then 3 are here. So so that 5 layers will create like the detector prototype. So this is actually a CAD design. So this is 1 layer, 2nd layer, 3rd layer, 4th and 5th. And this detector is kept on a kinematical mount so that the detector can rotate and detector can go up and down. And I can change the position from my laptop itself. So it is amazing to me, like even though my detector is halfway around the world, I can change it from here with just an internet connection. No, this is at SLAC, Stanford Linear Accelerator. Yeah. Yeah, the chip were made by Alice. We bought the chip from them, and then this is in SLAC. Okay, so now we did some data taking campaigns in November 2024. This was initial DAC optimization, and February 2025. This was toy signal positron from beryllium window. So what is that? I will show you. And then here we wanted to test the capability of the detector in detecting the positron tracks. So basically, what we said that see the rate of signal positrons, so that only came from simulation, and we have no idea if the simulation is correct or not. Okay, so that's why we want to see if my detector is detecting it correctly. We should actually test it for a situation where we already know the rate. Okay, so that's why what we did, we removed the laser, and then we use a beryllium window to block the electron beam. So then electron beam will fall on the beryllium window, and then it will give us Bremsstrahlung electron positron. So this is very, very well studied phenomena. So we know the rate that the positron will be created from beryllium window, and if we can get the same rate in our detector, so that will give us a faith that our detector is actually detecting positrons very well. Okay, so this is what we wanted to do in the beginning. So in today's talk, I will show the result from this February 2025 situation, and then eventually in May, November 2025 and March, June 2026, we actually took out the beryllium window and we turned on the laser. So this is the quest we are involved in. So the data are still being analyzed. So it's not public yet, so I cannot show you now. But see, I told you, like for simulation, we used Kalman filter algorithm, and there we need like very knowledge about the alignment. These are from data. These are like 5 layers. You see, if they are properly aligned, those layers, so then this hotspot should have been same in all 5 layers. But this is not what is happening. So because of the misalignment, so these are like, you understand, this is just so this is just a plug, we put it inside. So then this is like handmade, so it can have a problem of, say, micrometer range. So that is actually the misalignment that we find, and because of that we have to reconstruct using what is happening. Previously Kalman's filter algorithm, but here it is not Kalman filter, we cannot use because of the misalignment that we have. So we tried to seed using hue transform. So what is it? So hue transform is actually taking a point. So suppose this is a point in our tracker layer and we do hue transformation. So then this is the angle, then that will come out like a wave. Okay. So this one will come out like this wave, then this red one will come out like that wave, etc. Now, one beauty is that suppose these 5 lines, I mean 5 points, they all fall in the same straight line, then they will intersect at one point. Okay. I actually drew this black line, so black dot. So this is outside of the straight line. So then these black dots will not cross at the same point. So this is in x-axis, this is in y-axis. So this is a way to understand if 5 hits are actually falling on a straight line or not. So if I see this hue transformation of all the points, they actually cut at the same place, I will say they all 5 points are in a straight line. If they are not, so they will not fall in the straight line. Okay. So now we use this to understand which hits can be used as the track seed, and then we reconstruct the track. So here we did not use the Kalman filter algorithm. Yes. There will be, I actually did not show them. So when we actually did that, so there was a very broad region where we had the crossings. So we had to.
No, I don't have any time information, correct? Heats. You
We
have
do
only-
microsecond resolution. Microsecond
No,
resolution.
There will be a lot of points in those
Mhm.
5 data. I can have a straight line which are not